Hello everyone, my name is Mihir Jevdikar and I am applying for the Mathematics Masters program at Courant Institute at NYU. I received my BTech in Computer Science and Engineering from IIT Kanpur in 2021. Since then I have been working as a software engineer at Microsoft. So first of all, I'd like to talk about why an MS in mathematics and why a change in career. Mathematics has been my favorite subject since my school time, but I would say my real introduction to pure math was in my first year course, Real Analysis, and that course changed my perception towards math. It showed that calculus and mathematics in general, they are more than just tools to be used in engineering, and there are objects which are not necessarily in our physical universe, and we can talk about them, we can talk about their properties, and somehow some application always comes in our physical universe. And since then I pursued a lot of pure math courses and I've always enjoyed the rigor in them. And I want to pursue masters because I want to do a more such high level courses, and I want to understand these objects in a deeper level. One more reason is whenever I have talked to a mathematician or whenever I have read a book by a mathematician, I've always felt that these people know something which a layman doesn't know. And despite doing so many undergrad courses, whenever I go to a mathematician's website and if I just click on a research paper, there is hardly anything that I understand. And I don't want to be at that stage anymore. I want to understand things at a deeper level, and hence I want to do a master's followed by a PhD in mathematics. Coming to the second question, my favorite theorem in mathematics. This theorem is called theorem on projections. It's from set theory. Okay, and we will soon see that the same theorem appears under different names in different areas. So before going to the theorem, let's talk about some terminologies. Let A be a set and let tilde be an equivalence relation on A cross A. So for any element small a in A, we define the equivalence class as set of all elements in A which are equivalent with small a. And we also define a quotient set. Quotient set is collection of all such equivalence classes of elements in A. It is easy to see that quotient set will be a subset of par set of A. Furthermore, we define a projection function from A to the quotient set where we are mapping every element to its equivalence class. Now that the terminologies are defined, we can start the theorem. The theorem says let f be a function from A to B, and let define our equivalence relation as two elements in A are equivalent if and if their function takes same value. Now the theorem says then there is a unique function g from the quotient set to B such that f is composition of g and pi being the projection function. Furthermore, if f is a surjection, then g is a bijection. In other words, the quotient set, there is a bijection between quotient set and image of f. Now we will discuss what makes this theorem really interesting. So I have drawn the diagram here. So what we are saying, if we have a function from A to B, then there is a unique bijection g. The double arrows represent surjection and the curve represents an injection. So g is a bijection. So there is a unique bijection such that this diagram commutes. And why this is so important? Now consider our sets being replaced with groups G and H and a homomorphism, a group homomorphism phi. Now if we define our equivalence relation, the same equivalence relation, that A is equivalent to B whenever the homomorphism takes the same values, it is easy to see that the equivalence classes formed under this equivalence relation is same as the coset, same as this coset. In other words, what we are saying is the above diagram changes to this diagram and this diagram commutes. In other words, the quotient group G quotient kernel phi is isomorphic to image of G, and well, this is just the first isomorphism theorem in groups, and now we can replace these sets with rings, and with the same equivalence relation we'll get a ring isomorphism, and thus we have the first isomorphism theorem in rings. We can replace it with, replace the sets with vector spaces and the function with a linear transformation, and we have the same theorem, the isomorphism theorem for vector spaces. The quotient space is isomorphic to the image of L. The reason I like this theorem is what it's trying to say is it doesn't matter what stuff you are studying, whether you are studying groups, rings, vector spaces, or something else, as long as it has a certain structure, this theorem is going to hold true. And it sort of interconnects these seemingly different fields in algebra, and perhaps we can add a few more fields, like the theorem will hold true in an abelian category, or I believe in topology also there is an equivalent form, and and this brings me to the third question. Why MS at NYU? And I believe when you are studying higher mathematics, you will see a lot of such things which are talking about this interconnectedness, and your interest, one doesn't know what their interest will be. And Courant has a lot of people working on these interdisciplinary fields, and which I believe will help me. There are people working in physics, biology, computer science, statistics, pure maths, and so no matter where my interests lie after an year or two, I know there will be some people working in those areas. Thank you for considering my application.